Hello there, and welcome to Sleep Science Daily. Tonight, we are turning our attention to the red light in the night sky, the planet Mars. For thousands of years, people have noticed it, a point of light that glows with a faint rust color and moves slowly against the stars in a way nothing else does. Ancient astronomers tracked its wandering path. Entire civilizations named it after gods of war. And somehow, even now, it still stops people when they see it. Yet Mars is far more than a light in the sky. It is a real world with the tallest mountain in the solar system. Ancient riverbeds carved 3 billion years ago, ice buried beneath its surface, and robots already rolling across its plains. A world our species is preparing to walk on. Tonight we will wander through the science, the history, the machines we sent ahead, and the question that every Mars mission is quietly asking. If these gentle journeys give your mind somewhere quiet to rest, consider liking and subscribing to Sleep Science Daily. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do. Let your breathing slow, let your body soften, and let's begin. The red you see when you look up at Mars on a clear night is the color of rust. The soil is rich in iron, and over billions of years, that iron slowly oxidized the same quiet chemistry that turns an old nail red in the rain. An entire planet, rusting in the dark, for longer than life has existed on this one. When you look up and find that steady point of light, you are seeing the evidence of a world that has been slowly changing since before our sun had planets. And that world turns at almost exactly the same pace as ours. A Martian day lasts just 37 minutes longer than the one you are ending right now. The sun rises in the east and sets in the west. Shadows lengthen in the afternoon. The light softens toward evening, and then the long dark comes. In this one quiet way, Mars breathes like Earth, a rhythm carried across all that distance, still recognizable, still familiar, as if the two worlds learned the same habit long ago. Rising from that surface is the tallest mountain anywhere in the solar system. Olympus Mons climbs nearly 3 times the height of Everest, wide enough to cover an entire country. It built itself slowly over billions of years, through patient flows of lava, returning again and again to the same place. Because on Mars, the crust never moves, and the heat always came back. It stands quiet now, enormous and still, rising from the red plains into a sky so thin it is almost space. The largest mountain anywhere, shaped not by violence, but by time. And cutting through that same surface is the deepest canyon in the solar system. Valles Marineris did not form the way canyons form on Earth. No river carved it over centuries. The ground simply cracked open, pulled apart by the same volcanic forces that built Olympus Mons nearby. The result stretches as wide as a continent, deep enough that clouds form inside it, walls so far apart the other side sits beyond the horizon. It is not a wound. It is an opening, ancient and patient, into the interior of another world. Above that world, 2 small moons move through the dark. Phobos and Deimos are nothing like the grand companion that circles Earth. They are small and irregular, shaped more like tumbling rocks than proper moons. Phobos moves so quickly that it rises and sets 3 times in a single Martian day. Deimos, farther away, looks from the surface like nothing more than a bright wandering star. And Phobos is falling, spiraling closer to Mars with each passing year. destined in millions of years to crash or shatter into a ring. Even the moons of Mars are impermanent. Even up there, nothing holds forever. Below those moons, the planet tilts at almost exactly the same angle as Earth. And so it too has seasons: summer and winter, spring and autumn. But a Martian year is nearly twice as long as ours, and so each season stretches for months. In the depths of a polar winter, the temperature drops so far that carbon dioxide freezes out of the atmosphere and falls as dry ice snow onto the ground. In spring, it sublimates back into gas, and the ice caps breathe outward again. The rhythm is familiar. Only the patience required to live inside it is different. Look up at the sky during the day on Mars, and it will not be blue. The thin air is full of fine red dust that never fully settles, and it scatters light into a pale butterscotch glow that lasts from sunrise to sunset, warm and amber and quiet. But as the sun goes down, something unexpected happens. The sky around it turns blue, the color it never shows during the day, glowing softly before the dark comes. On Mars, the colors are reversed. Daytime is warm, sunset is blue. It is beautiful in a way that belongs entirely to itself. At both poles of that world, white gleams against the red. Ice, growing and shrinking with the seasons, visible from Earth through a telescope. The winter caps are mostly frozen carbon dioxide, the atmosphere itself crystallizing in the cold. But underneath lies something older. Water ice, compressed and ancient, preserved through billions of years of Martian winters. The South Polar Cap alone holds enough water that if it ever melted, it would wash across the entire planet in a shallow sea. That water is not going anywhere. It rests in the cold at the bottom of the world, still and patient. Mars is half the size of Earth. Hold the two planets side by side, and Mars would fit inside Earth almost 7 times over. That smaller size shaped everything: the thinner air, the weaker gravity, the inability to hold on to warmth and water over geological time. Mars was simply too small to keep what it had. What it once was, warmer and wetter and full of possibility, has been slowly slipping away for billions of years, carried off grain by grain into the dark. That smaller world pulls at you with only 38% of the force Earth does. Every step you took would carry you farther. Every jump would lift you higher. At first, it might feel like freedom, and in some ways it would be. But the body does not experience low gravity as a gift for long. Bones begin to lose their density. Muscles quietly forget how hard they once had to work. Someone who lived on Mars for years might return to Earth and find its pull almost unbearable. The world that once felt like home, now pressing down like something they no longer recognized. The year on that world lasts nearly twice as long as ours. Mars orbits the Sun at a greater distance, along a longer path, completing one full circle in 687 of our days. Seasons stretch, winters linger. Summers are long and low and cool. Time on Mars moves at the same pace as time anywhere, 1 second at a time, 1 breath at a time, only measured against a slower, wider turning of the world beneath your feet. Every few Martian years, the dust wakes up. A storm gathers somewhere on the surface and grows, and finds another storm, and slowly spreads until the entire planet disappears beneath a curtain of fine red particles kilometers high, blocking the sun for months. In 2018, one of these storms settled over the rover Opportunity. Its solar panels fell dark. Its last signal home carried the news that its power was low and the light was fading. It never woke up again. The dust on Mars is patient and thorough. In the end, it covers everything. What allowed those storms to grow so large is the same thing that allowed Mars to lose so much of itself, the absence of a magnetic field. Earth is wrapped in an invisible shield, generated deep in its molten core, deflecting the solar wind and protecting the atmosphere. Mars lost its field billions of years ago when its smaller core cooled and went still. Without protection, the solar wind stripped the atmosphere away, particle by particle, over millions of years. Not a catastrophe, a fading quiet and complete and irreversible. And in that thin, unprotected air, temperatures swing nearly 100 degrees between midday and midnight. The moment the sun sets, what little warmth the day built bleeds away into space. Almost instantly, there is nothing left to hold it. The rocks live through this every single day, warming and cooling, expanding and contracting, slowly wearing down over billions of years. Everything on the surface of Mars carries the mark of this endless oscillation between the brief memory of warmth and the long, cold fact of the dark. 3 billion years ago, Mars was wet. Not damp or frozen at the edges, but genuinely, abundantly wet, with rivers running across its surface, lakes filling the low places between craters, and perhaps an ocean covering the entire northern hemisphere to a depth of hundreds of meters. We know this not from guesswork, but from the landscape itself, which still carries the memory of water in every valley and lakebed and mineral deposit. Mars was not always the world it is now. Something changed, and the evidence of what it once was is still there, waiting in the rock. Those rivers carved the surface in ways that are unmistakable. Valley networks spread across the southern highlands, like the branching of a great tree channels that once carried water downhill toward the low northern plains, some stretching for thousands of kilometers. Some show the gentle meandering of a river that had time to slow and turn and find its own way. They did not form overnight. They formed over millions of years, in a climate warm enough and wet enough to sustain them. A climate that is gone now, but not forgotten. Where the water collected, it left sediment behind. In crater after crater across the Martian surface, layers of fine-grained rock have been found, the kind that only settles out of still water, slowly, over time. These are the floors of ancient lakes, some of which may have persisted for thousands of years. Jezero Crater, where the Perseverance rover landed in 2021, is one of them. A river once flowed in from the west and deposited a fan of sediment across the crater floor like a delta in slow motion. From orbit, it looks almost like something from Earth, a place where water once rested and then did not. The minerals tell the same story. Scattered across the surface are deposits of clay and carbonate and sulfate minerals that only form when liquid water interacts with rock over long periods of time. Clay minerals, in particular, require patience. They form slowly, as water works its way through stone, breaking it down, reorganizing its chemistry over thousands of years. Their presence on Mars is not subtle. It is a signature, clear and persistent, of a world that once had water in abundance and held it long enough for chemistry to begin. Some of that water is still there. At both poles, buried beneath layers of dust and dry ice, ancient water ice sits compressed and preserved. And not only at the poles, radar instruments aboard orbiting spacecraft have detected layers of water ice buried in the soil at mid-latitudes, mixed into the ground like a hidden reservoir waiting beneath the surface. Mars did not lose all of its water to space. Some of it retreated underground, where it has been frozen ever since, patient and still, in the dark beneath our feet. In 2018, a radar instrument aboard the European Mars Express spacecraft found something unexpected beneath the South Polar ice cap, a zone of unusually bright reflections, about 20 kilometers across, buried more than a kilometer beneath the surface. The best interpretation was a subglacial lake, liquid water, kept from freezing by the pressure of the ice above and perhaps by salts dissolved within it. Not warm, not welcoming, but liquid, on Mars, right now. That single discovery changed the conversation about what Mars still holds. The question that follows that discovery is quiet and enormous. If liquid water exists beneath the surface of Mars today, even cold and dark and saturated with salt, could something be living in it? Life on Earth has been found in places almost as inhospitable, deep in Antarctic ice, in acidic volcanic springs, in the lightless vents of the ocean floor where no sunlight has ever reached. Life, once it begins, is remarkably reluctant to stop. Whether it ever began on Mars is the question that no instrument has yet been able to answer. Mars lost its water slowly, not all at once. The process began when the magnetic field faded and the solar wind started stripping the atmosphere away. As the atmosphere thinned, the pressure at the surface dropped, and as the pressure dropped, liquid water became unstable, unable to exist on the surface without immediately boiling away or freezing. The rivers stopped, the lakes evaporated, the ocean, if there was one, retreated first to ice and then to vapor, carried away molecule by molecule over hundreds of millions of years, into a sky that could no longer hold it. What remained was mostly carbon dioxide, the gas that makes up 95% of the Martian atmosphere today. Not breathable, not warm, but a record, nonetheless. The air of Mars is the remnant of something richer, something that once included enough water vapor and warmth for rivers to run and lakes to fill. That atmosphere is mostly gone now, thinned to less than 1% of Earth's, too sparse to protect the surface or hold the heat of a distant sun. What we breathe in our lungs every second, Mars lost over geological time. Quietly, completely, irreversibly, and yet the search is not over. Beneath the surface, sheltered from radiation and the cold, water may persist in forms we have not yet fully mapped. The ice, buried at mid-latitudes. The possible lake beneath the southern pole. Minerals that still contain water locked inside their crystal structure, waiting. Mars has not given up all of its water. It has only hidden it deeper and colder and further from the surface, in places that will require human hands, or at least human ingenuity, to reach. The water is still there. We just have to find it. What those hidden waters might contain is the question that drives every mission we send to Mars. Not because we expect forests or oceans or creatures looking back at us, but because even the smallest trace of past or present life on Mars, a fossil, a chemical signature, a single strand of something biological preserved in ancient rock, would be the most significant discovery in the history of science. It would mean that life is not a miracle that happened once, by chance, on one small planet. It would mean that wherever water and energy and the right chemistry come together, something stirs. It would mean that the universe is far more alive than the silence of the night sky has ever led us to believe. Mars is a planet of two faces. Draw a line around its middle, and the two hemispheres look almost nothing alike. The northern half is flat and low and young, a vast, smooth plain that may once have been the floor of an ancient ocean, swept clean by water and time. The southern half is ancient and heavily cratered, scarred by billions of years of bombardment, its surface a record of everything that has ever hit it. Two different worlds sharing one planet, divided by a boundary that scientists are still trying to explain. Nowhere else in the solar system is the contrast between two hemispheres so sharp, so complete, so strange. The northern plains sit lower than almost anywhere else on Mars. In some places, they lie several kilometers below the average elevation of the planet, a vast depression that would have made a natural basin for any water flowing down from the ancient southern highlands. From orbit, the surface looks smooth, almost featureless, as if something once filled it and then drained away. Which is exactly what many scientists believe happened. The northern plains may be the ghost of an ocean, its floor preserved beneath the dust, still holding the faint outline of ancient shorelines that once marked the edge of a Martian sea. The southern highlands remember further back. Some of the craters there are among the oldest surfaces in the solar system, their rims worn soft by billions of years of wind and dust, but still unmistakably there, still marking the places where ancient impacts struck a world that was already old. These craters have not been erased by tectonics, or covered by lava, or washed away by rain. They simply remain patient and permanent, the way only things on airless worlds can remain. The southern highlands of Mars are one of the oldest landscapes in the solar system, a surface that has barely changed since the early days of everything. Buried within the southern hemisphere is the largest impact basin anywhere on Mars. Hellas Planitia stretches more than 2,000 kilometers across and plunges nearly 8 kilometers deep, deep enough that the atmospheric pressure at its floor is higher than anywhere else on the planet, high enough that liquid water might briefly exist there under the right conditions. From the rim of Hellas, if you could stand there, the far wall would be over the horizon. The basin is so large it has its own weather, its own dust patterns, its own slowly cycling atmosphere, an entire world within a world, carved out by a single collision long ago. Beneath the surface of Mars, lava tubes may stretch for hundreds of kilometers. Where volcanic activity once flowed, it left behind tunnels, hollow channels where lava rivers once ran and then drained away, leaving the hardened roof intact above an empty corridor. On Earth, these tubes can be large enough to walk through. On Mars, where gravity is weaker and ancient eruptions may have been far more powerful, they could be enormous, wide enough to shelter entire cities, deep enough to shield anything inside from radiation and temperature extremes. These tubes are among the most promising places scientists have considered for future human habitation. The surface of Mars is hostile. What lies beneath it may be livable. The soil of Mars contains a problem. Mixed throughout the Martian surface are compounds called perchlorates, salts of chlorine that on Earth are used in rocket fuel and are toxic to human biology in significant concentrations. Any future colonist who tried to grow food in unprocessed Martian soil would face serious challenges because perchlorates interfere with the thyroid and can accumulate in the body over time. The dust that blows across the surface carries these compounds everywhere. They coat the rocks, fill the air during storms, settle on every surface. Mars is beautiful, and it is hostile in ways that are not always visible. The ground itself pushes back. At a microscopic level, Martian dust is sharp. On Earth, grains of sand and soil are worn smooth over time by water and wind and the constant grinding of geological processes. On Mars, without water to soften them, dust particles remain angular and jagged, their edges preserved exactly as they formed. This dust gets into everything, into rover wheels, into instrument joints, into the lungs of any living thing that might breathe it. Astronauts on Mars would need to manage dust with a seriousness that goes beyond inconvenience. It is a fine, pervasive, cutting presence that covers the entire planet and never stops moving. The dust smells of gunpowder. This is not a guess. It is the reported experience of astronauts who handled lunar soil, which shares some chemical similarities with Martian regolith. When the oxidized minerals in extraterrestrial dust come into contact with the moisture of human airways, they produce a sharp, metallic scent that early Apollo astronauts described immediately. No human has yet breathed Martian air, of course, but the chemistry suggests that if you stepped inside a habitat after a walk on the surface and removed your helmet, the first thing you might notice, beneath everything else, would be something that smells like a match just struck. The entire planet, carrying the scent of ancient fire. Across the surface of Mars, dust devils roam constantly. These are not gentle whirlwinds. Some rise several kilometers into the thin air, spinning columns of red dust that move across the plains in slow, wandering paths, visible from orbit as dark tracks left across the lighter surface. The Opportunity rover once had its solar panels cleaned by a passing dust devil, a lucky stroke that extended its life when the accumulated dust was threatening to starve it of power. On Mars, dust devils are not a curiosity. They are a feature of daily life. One of the ways the planet keeps itself in motion, redistributing its surface, grain by grain, across the centuries. The sand dunes of Mars move. Slowly, measurably, verifiably, dunes shift position from year to year, driven by the Martian wind across the floors of craters and the slopes of ancient valleys. Some dunes are dark, made of volcanic basalt sand ground fine over geological time. Others are pale, made of dust so light it hangs in the air for months. Orbital cameras have photographed the same dunes in different seasons and watched them migrate, watched their slip faces shift direction, watched the same grains that have been moving across Mars for millions of years continue their quiet journey. The surface of Mars is never fully still. The crust of Mars is thick and ancient and unbroken by the kind of plate tectonics that constantly reshapes the Earth. On our planet, the crust is divided into moving plates that drift, collide, and subduct, recycling the surface, erasing old features, and building new ones. Mars has none of this. Its crust formed and then stayed, holding the record of everything that happened to it without the planet's own geology erasing the evidence. This is partly why Olympus Mons grew so tall and Valles Marineris stretched so wide there was nothing to interrupt them, nothing to move the crust away from the heat source, nothing to close the fracture. Mars is a planet that remembers everything. Deep within that crust, Mars still trembles. The InSight lander, which touched down in 2018 and operated for 4 years, detected hundreds of Marsquakes during its mission tremors, generated not by plate tectonics, but by the slow cooling and contracting of the planet's interior, ancient faults shifting under the accumulated stress of billions of years. Most were small, barely detectable. A few were significant enough to ring the planet like a bell, sending seismic waves traveling through the crust that InSight could use to map the interior. Mars is not geologically dead. It is geologically old and settling, like a house still shifting on its foundations long after it was built. At the heart of Mars, the core has gone quiet. Early in the planet's history, its core was molten and churning, generating the magnetic field that once protected its atmosphere. But Mars is smaller than Earth, and small worlds cool faster. The churning slowed. The magnetic field faded. The core solidified, or partially solidified, into a state that generates no protective shield and provides only faint echoes for the seismic instruments that try to read it. InSight's measurements suggested the core is larger than expected and may be partially liquid still, mixed with lighter elements that lowered its melting point. A core that is neither fully alive nor fully dead, sitting at the center of a world still working out what it has become. And still, faintly, Mars breathes. Instruments have detected trace amounts of gas being released from the Martian surface and subsurface outgassing from minerals, from ice, from processes we do not yet fully understand. Methane appears and disappears in the atmosphere in amounts too small to see, but large enough to measure, varying with the seasons in ways that suggest an active source somewhere beneath the surface. The planet is not entirely passive. Somewhere inside it, chemistry is still happening. Reactions are still occurring. Something is still moving in the dark, deep beneath the dust, in a world that looks from the outside like it stopped long ago. The first spacecraft to reach Mars arrived in 1965, and what it found changed everything. Mariner 4 flew past the planet and sent back 22 photographs, grainy, black and white, barely recognizable as images at all. But they were enough. They showed a cratered, barren surface with almost no atmosphere, no canals, no vegetation, no sign of the civilization some had dared to imagine. The scientists who had waited years for those pictures went quiet. Mars was not what anyone had hoped. It was older and emptier and harder than the dreams that had been built around it, but it was real. And that, in the end, was enough to keep looking. The Viking landers arrived in 1976 and did something no spacecraft had done before. They landed softly on the surface of another planet and stayed. Viking 1 touched down in July of that year. Viking 2 followed 2 months later. Together, they photographed the landscape, measured the weather, and scooped up samples of Martian soil to test for signs of life. The results were strange. Some experiments produced reactions that looked almost biological, then didn't. The debate over what Viking found has never fully been resolved. Scientists still argue about it today. The landers that were supposed to answer the question of life on Mars instead produced a question that has outlasted everyone who designed them. In 1997, something small and six-wheeled rolled off a ramp and onto the surface of Mars for the first time. Sojourner was no larger than a microwave oven, and it moved at a pace that made patience feel like speed. But it worked. It rolled across rocks, pressed its instruments against them, and sent data back across the void to a world watching on the early internet in numbers no one had anticipated. Pathfinder and Sojourner turned Mars from a destination into something closer to a place somewhere you could picture yourself standing, looking at the same rocks the rover was touching, separated by nothing but distance and time. Spirit and Opportunity landed in January 2004 with a planned mission of 90 days. 90 days was considered optimistic. The dust would accumulate on the solar panels, the engineers said. The batteries would fade. The cold would take its toll. Spirit lasted 6 years before it drove into soft sand. It could not escape. And after months of silence, NASA declared the mission over. It had driven more than 7 kilometers across a landscape no human eye had ever seen directly. 90 days became 6 years. The rover that was supposed to last a season became something closer to a companion. Opportunity did not stop at 6 years. It kept going through dust storms, through Martian winters, through 1 year and then another and then another, until 15 years had passed, and it was still moving, still sending data, still finding things no one expected to find. It drove more than 45 kilometers across the surface of Mars, descended into craters, climbed out again, and outlasted every prediction made about it by a margin that still seems impossible. Then, in 2018, a global dust storm settled over it. The panels went dark. The last signal Opportunity sent home reported that its battery was low and the sky was extremely dark. It was never heard from again. 15 years, 45 kilometers, and then silence. Curiosity landed in August 2012 inside Gale Crater, a place chosen because it contained a mountain made of layered sediment, billions of years of Martian history, stacked in rock that Curiosity could drive through, like reading pages of a book. It is still there, still roving, still drilling into the surface and analyzing what it finds. Curiosity has confirmed that Mars once had the chemistry necessary for life, found organic molecules in the rock, and measured radiation levels that tell us exactly how dangerous the journey to Mars will be for the humans who eventually make it. It has been driving for more than a decade across a world that no human has ever stood on. It will likely still be there when the first one does. Perseverance landed in Jezero Crater in February 2021, in a place that scientists believed was once the floor of an ancient lake. It carried with it the most sophisticated instruments ever sent to Mars, instruments designed not just to study the planet, but to collect samples of its rock and set them aside, sealed and labeled, waiting for a future mission that will someday bring them back to Earth. Those samples are sitting on the surface of Mars right now. Sealed tubes of ancient Martian rock sitting on the ground inside a crater that was once underwater, waiting for someone to come and get them. The most carefully chosen pieces of another world, patient in the cold. Tucked inside the belly of Perseverance was a small helicopter called Ingenuity, weighing less than 2 kilograms, with blades that had to spin 5 times faster than a helicopter on Earth just to generate enough lift in the thin Martian air. On the 19th of April, 2021, Ingenuity lifted off the surface of Mars and hovered for 39 seconds. It was the first powered, controlled flight by an aircraft on another planet. The Wright brothers' first flight at Kitty Hawk lasted 12 seconds. Humanity went from that to flight on another world in just over a century. Ingenuity was supposed to fly 5 times. It flew 72 before its final landing damaged a rotor blade. 72 flights. En masse. Also aboard Perseverance was an instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. It did something small and extraordinary. It took carbon dioxide from the Martian atmosphere and converted it into oxygen. Not a large amount, roughly enough for a few minutes of breathing. But the principle was proven. The raw material for oxygen exists on Mars in abundance. The technology to extract it works. Any future human mission that needs oxygen for breathing, for rocket fuel, for survival, does not need to bring all of it from Earth. Mars can make it. The planet itself can sustain what comes to live on it. From orbit, spacecraft have mapped every centimeter of the Martian surface. Cameras have photographed individual boulders from hundreds of kilometers above. Radar instruments have peered beneath the surface. Infrared sensors have mapped the temperature of the ground hour by hour through the Martian day. Spectrometers have identified minerals in rock formations from space. We know the shape of Mars better than we knew the shape of Earth a century ago. We have more detailed maps of a world no human has visited than explorers of the 19th century had of their own planet. Mars is in some ways the most thoroughly studied place in the solar system after Earth itself. The robots on Mars are our first presence on another world. They are not alive, but they carry the fingerprints of everyone who built them, the engineers who stayed up through the night, the scientists who spent careers waiting for data, the people who watched landings through their fingers and wept when the signal came through. Every rover that has driven across that surface, every lander that has sat in the wind, every orbiter that has circled silently overhead, they are all extensions of something human, sent ahead into a place we could not yet go ourselves. They went first. They made it possible. And somewhere on the surface of Mars, right now, one of them is still moving. Mars is not always the same distance away. At its closest, it comes within 54 million kilometers of Earth, near enough that its rust-colored glow brightens noticeably in the night sky. At its farthest, it drifts to more than 400 million kilometers away, a point of light so distant it barely differs from the stars around it. The distance between the two planets is never fixed because both are moving, orbiting the Sun at different speeds along different paths, sometimes drawing close and sometimes pulling apart. Every mission to Mars must be planned around this dance, launched at precisely the right moment to intercept a world that will not be where it is now by the time the spacecraft arrives. The journey itself takes between 6 and 9 months, depending on the trajectory chosen. 6 months of travel through a void that contains almost nothing, no air, no weather in any familiar sense, no landmarks, no way to stop or turn back. The spacecraft moves in a long, curving arc called a Hohmann transfer orbit, coasting on the momentum of its launch, carried forward by physics rather than thrust. The crew inside would watch Earth shrink to a point of light within days. They would watch Mars grow slowly, brighter, over months. And for most of the journey, they would be neither here nor there, suspended between two worlds, in a silence that has no equivalent anywhere on Earth. Launch windows open only once every 26 months. This is the interval at which Earth and Mars align closely enough for the journey to be practical, when the orbital geometry is favorable and the fuel cost is manageable. Miss the window, and the next one is more than 2 years away. There is no flexibility in this, the way there is in almost every other kind of travel. No changing your departure date, no rescheduling for better conditions. The planets move on their own schedule. Every Mars mission in history has been built around this constraint. The 26-month window is not a detail of space travel. It is one of its defining rhythms. During those months of travel, the human body would begin to change. In the weightlessness of deep space, bones lose density because they no longer need to bear weight. Muscles weaken because they no longer need to resist gravity. The spine lengthens. Fluid shifts toward the head, putting pressure on the eyes in ways that can affect vision permanently. Balance systems that evolved over millions of years to work in gravity begin to drift without it. Astronauts on the International Space Station follow rigorous exercise regimens for 2 hours every day just to slow this deterioration, and still return to Earth needing months of rehabilitation. The journey to Mars would be 3 times as long as the longest stays on the station. Radiation is the threat that doesn't announce itself. On Earth, the planet's magnetic field and atmosphere absorb the constant stream of charged particles flowing outward from the Sun and in from the wider galaxy. In deep space, there is no such protection. Cosmic rays pass through the walls of a spacecraft and through the bodies of anyone inside. Over months of travel, the accumulated dose would be significant, raising the lifetime risk of cancer, potentially damaging the central nervous system, possibly affecting cognition and behavior in ways researchers are still working to understand. Shielding helps but adds mass, and mass is the enemy of everything in spaceflight. Radiation is the problem that every Mars mission plan must account for, and that none has yet fully solved. A message sent from Mars takes between 3 and 22 minutes to reach Earth, depending on where the two planets are in their orbits. A question asked from the surface of Mars will not receive its answer for at least 6 minutes, and sometimes for nearly 45 minutes round trip. There is no real-time communication possible. No calling home to ask for advice in the moment. No mission control talking a crew through a crisis as it unfolds. Every decision made on Mars will be made by the people on Mars, with the information available to the people on Mars, in the time available to the people on Mars. The distance is not just physical, it is a transfer of responsibility unlike anything in the history of human exploration. Once a crew leaves Earth's orbit heading for Mars, there is no practical way to turn back. The trajectory that carries a spacecraft toward Mars does not allow for a simple reversal. The fuel required would be enormous, and even if it existed, the window for return might not be open. In the early days of the mission, if something went wrong, the crew would be on their own in a way that no astronaut has ever been before. The Apollo 13 crew, crippled in space, could reach Earth in 4 days. A crew bound for Mars would have no such option. Whatever they carried with them, in equipment, in knowledge, in each other, would be all they had. Landing on Mars is described by engineers as 7 minutes of terror. The spacecraft enters the atmosphere at nearly 20,000 kilometers per hour. It has approximately 7 minutes to slow to a stop before hitting the ground, and during those 7 minutes, it is entirely on its own. The communication delay means that by the time a signal confirming entry reaches Earth, the landing is already over, one way or the other. The atmosphere is thin enough that it barely helps with braking, but thick enough to generate enormous heat. Parachutes alone cannot slow a large spacecraft in time. Every Mars landing in history has required a different combination of heat shields, parachutes, retro rockets, and in one extraordinary case, a sky crane that lowered a rover on cables from a hovering descent vehicle. Nothing about landing on Mars is easy. The thin atmosphere creates a problem that begins before landing and continues after arrival. Mars air is so sparse, less than 1% of Earth's atmospheric pressure, that a parachute that would work perfectly on Earth barely functions there. Designing landing systems for large, crewed spacecraft is one of the unsolved engineering challenges of Mars exploration. The rovers we have landed there are small. A crewed lander would be orders of magnitude heavier, and the same systems that gently set down a 1-ton rover would be wholly inadequate for what human Mars exploration will require. The problem is known. The solution is still being worked out. Making fuel on Mars may be the only practical way to get home. Carrying enough propellant from Earth for both the journey to Mars and the return trip would make the spacecraft so heavy that launching it would require rockets far beyond anything currently in existence. The alternative is to make the return fuel on Mars itself using the carbon dioxide in the atmosphere and water extracted from the soil to produce methane and oxygen through a chemical process that works reliably in the plain side. Laboratory. MOXIE aboard Perseverance proved the oxygen half of this equation already. A future mission might send a fuel production plant to Mars years before the crew arrives, so that by the time humans land, their ticket home is already waiting. The planet that seems so hostile turns out to hold the ingredients for departure. The first humans to travel to Mars may not come home. This is not speculation, it is a possibility that mission planners and astronaut candidates discuss openly. The risks of the journey, the uncertainty of the landing, the unknowns of living on the surface, the difficulty of the return, any one of these could fail. Some of the people who have volunteered for Mars missions have done so knowing that the odds of a one-way outcome are real. They volunteered anyway. This is not recklessness. It is the same calculation that every explorer in history has made when stepping towards somewhere genuinely unknown, that some destinations are worth the risk of not returning, that the value of going outweighs the cost of staying, that there are things more important than coming back. A habitat on Mars would need to be built mostly underground. The surface is too exposed to radiation, to temperature swings, to the abrasive dust that works its way into everything. Underground, the rock itself provides insulation and shielding. The temperature is more stable. The cosmic rays that stream through the thin Martian atmosphere are absorbed by the meters of soil above. Every serious design for a Mars habitat begins with the same conclusion that the planet's surface, for all its stark beauty, is not where humans can safely live for long. The first Martian homes would be buried, pressurized chambers of warmth and air carved into a world that offers neither. People would live beneath the ground of a planet, looking up at a sky they could not breathe. Lava tubes may make this easier than it sounds. Beneath the volcanic plains of Mars, ancient channels where lava once flowed have left behind hollow tunnels, some potentially hundreds of meters wide and kilometers long. Their ceilings intact, their interiors naturally shielded from radiation and weather. Seal the entrance, pressurize the interior, and a lava tube becomes something close to a ready-made habitat, large enough for crops, for living spaces, for the small enclosed world that a colony would need to be. Scientists have identified candidate tubes from orbital imagery, their collapsed sections visible from space as long chains of depressions in the surface. The planet that seems to offer nothing may have already prepared the rooms. Growing food on Mars would be one of the central challenges of any long-term settlement. The soil contains perchlorates that must be removed before planting. There is no liquid water on the surface. The light from the sun, already weaker than on Earth, is further reduced by the ever-present dust in the atmosphere. Crops would need to grow under artificial light, in carefully managed environments, in soil that has been processed and supplemented, and watched over with a level of attention that farming on Earth never requires. And yet, it can work. NASA experiments have shown that plants can grow in simulated Martian soil when the toxic compounds are removed and nutrients are added. It will not be easy. It will be necessary. Water on Mars would come from ice extracted from the frozen ground, melted, filtered, and recycled with a completeness that no water system on Earth approaches. Every drop would matter. Every molecule of water vapor lost to the thin air would be a small defeat. The systems that manage water in a Mars habitat would need to recover it from breath, from sweat, from every process that releases moisture, and return it to the supply. Astronauts on the International Space Station already drink water recycled from their own urine, a fact that sounds unpleasant until you understand that the recycled water is cleaner than most tap water on Earth. On Mars, this kind of closed-loop thinking would not be a choice. It would be the foundation of survival. Every breath on Mars would cost energy. The oxygen that fills a habitat would need to be produced continuously, extracted from carbon dioxide using power-hungry chemical processes, or electrolyzed from water, or generated by some combination of both. The moment that process stops, the air inside begins to change. Carbon dioxide accumulates, oxygen depletes. The margin between breathable and fatal is measured in hours. This is the reality that every Mars settler would live with in a way that no one on Earth has ever had, to the knowledge that the air they are breathing was made, that it will run out if something fails, that the systems keeping them alive require constant attention, and constant power. Breathing on Mars would be an act of engineering as much as biology. The human body would change on Mars and not entirely come back. In 38% gravity, bones and muscles adapt to a lighter load. Over months and years, the body becomes optimized for Mars' lighter, more efficient in low gravity, calibrated to a world that asks less of it physically. This adaptation is a slow process and mostly invisible from the inside. But anyone who spent years on Mars and then returned to Earth would feel the difference immediately and painfully. Earth's gravity, which once felt like nothing at all, would become a weight pressing down on bones that had quietly forgotten how to carry it. The longer the stay, the harder the return. At some point, the body crosses a threshold from which coming back becomes not impossible, but genuinely dangerous. Children born on Mars would grow up in 38% gravity, and their bodies would develop accordingly. Their bones would form in a lower gravity environment. Their cardiovascular systems would calibrate to a different demand. Their muscles would grow strong enough for Mars, but not for Earth. A child raised on Mars might never be physically capable of visiting the planet their parents came from, might never stand under an open sky, feel rain, breathe unfiltered air. Earth would exist for them the way a distant country exists for someone who has only read about it. Real, vivid in imagination, but inaccessible in body. The first generation born on Mars would be, in a biological sense, the first humans who were not from Earth. Time on Mars would feel different. The Martian day is close to ours, 24 hours and 37 minutes. But that 37 minutes compounds over weeks and months into a slow drift away from any Earth-based schedule. Mission planners have already grappled with this. The scientists operating rovers on Mars often shift their sleep schedules to match Martian time, gradually falling out of sync with everyone around them on Earth. In a permanent settlement, the choice would eventually be made to live on Martian time, entirely to let the rhythms of another world replace the ones evolution built into human biology over millions of years. The body keeps its own calendar. On Mars, that calendar would need to be rewritten. The silence on Mars is deeper than any silence on Earth. Earth is never truly quiet. There is always wind in trees, or distant traffic, or the sound of other living things, or the low hum of the atmosphere itself. Mars has almost no atmosphere to carry sound, and what little air exists transmits it differently. Higher frequencies are absorbed, lower ones travel strangely, and the overall effect is a muffled, reduced, deeply unfamiliar quiet. Astronauts who have experienced the near silence of spacewalks describe it as disorienting. On the surface of Mars, the silence would be total in a way that no training can fully prepare a human being for. The mind that evolved in a world full of sound would have to learn to rest inside a world that has almost none. Sunsets on Mars are blue. During the day, the sky glows pale amber and butterscotch, the dust scattering the longer wavelengths of light and warming everything with a color that has no equivalent in any Earth sky. But as the sun descends toward the horizon, the scattering reverses. The blue light that was suppressed all day begins to dominate around the fading sun, and for a few minutes before darkness, the sky near the horizon glows a deep, vivid blue, the color the Martian sky never shows at noon. Rover cameras have photographed this phenomenon, and the images stop people. They expect alien and strange. What they see instead is beautiful in a way that feels almost familiar, almost like home, but filtered through something irreducibly other. On a clear night on Mars, Earth would be visible in the sky. Not as a planet with visible features, but as a bright blue-white star, the most vivid object in the Martian night after the sun and the moons. You could look up from the surface of another world and see the planet you came from, small and perfect and impossibly far, the way travelers used to look back at their home countries from ships in the middle of the ocean. Everyone who has ever lived, every city ever built, every war ever fought, every song ever sung, all of it contained in a single point of blue light hanging in the dark above a rust-colored horizon. The first person to see that view will understand something about being human that cannot be understood from anywhere on Earth. Mars would become home, slowly, without announcement. Not in any single moment, but across the accumulated weight of ordinary days, the particular color of the light in the afternoon, the sound of the habitat at night, the view from a certain window, the smell of the recycled air, the low gravity that would begin to feel less like a novelty and more like the way things simply are. Home is not the place you come from. It is the place your body learns to expect. Mars would be strange for a long time, and then it would not be strange. And then one day, someone would step outside and look around at the red plains and the amber sky and feel, without intending to, that they were exactly where they belonged. 3 billion years ago, the conditions on Mars were not so different from the conditions on early Earth. The same period when life first appeared in Earth's oceans, simple, microscopic, barely distinguishable from chemistry. Mars had liquid water on its surface, a thicker atmosphere, and enough warmth for the basic reactions of biology to begin. We do not know if they did, but we know that the ingredients were there, that the window was open, and that 3 billion years is long enough for life to have found its footing. On Earth, it only needed to happen once. The question for Mars is whether once was enough, and whether anything that began there survived what came after. The most likely place for life to have existed on Mars is not the surface, but beneath it. When the atmosphere thinned and the surface became hostile, any life that had started in the warm, shallow lakes and rivers would have faced a choice that life on Earth has faced many times: adapt or disappear. Some of it may have retreated, downward, into the rock, into the groundwater, into the deep subsurface where liquid water may still exist, and where the temperature is stable and the radiation from space cannot reach. Life in the deep rock of Earth survives without sunlight, without warmth, feeding on chemical energy from the rock itself. If anything similar took hold on Mars 3 billion years ago, it might still be there, reduced, slowed almost to stillness, but present. The surface of Mars preserves its past. Without plate tectonics to recycle the crust, without oceans to dissolve ancient rock, without the biological activity that on Earth constantly transforms the landscape, Mars holds on to things. Ancient lake beds remain intact. Ancient riverbeds still trace their paths across the southern highlands. Minerals that formed in the presence of water billions of years ago sit undisturbed in outcrops that rovers can drive up to and drill into. If life existed in those ancient lakes and rivers, it may have left traces in the sediment, fossilized structures, chemical signatures, patterns in the rock that biology produces and chemistry alone does not. Those traces, if they exist, are waiting in the rock of Mars, preserved in a world that is very good at keeping things exactly as they were. Perseverance is collecting those rocks. Sealed inside small titanium tubes, carefully selected samples of Martian sediment and ancient lakebed material sit on the surface of Jezero crater, waiting for a mission that will retrieve them and bring them back to Earth. This is the Mars Sample Return Campaign, one of the most ambitious projects in the history of planetary science. Years in planning and years still from completion. When those samples finally arrive in terrestrial laboratories, scientists will have access to tools and techniques that no rover could carry, instruments capable of detecting chemistry at levels of sensitivity that would be impossible on Mars, capable of seeing structures too small and too subtle for anything we have yet sent to the surface. The answer to the question of life on Mars may already be sitting in those tubes. Some Martian rocks have already come to Earth without our help. Over billions of years, large impacts on Mars have blasted pieces of the planet's surface into space with enough velocity to escape Martian gravity. Some of those pieces have drifted through the solar system and eventually fallen onto Earth as meteorites. We have identified more than 100 of them rocks whose chemistry matches what we know of the Martian crust, carrying inside them tiny bubbles of ancient Martian atmosphere and grains of Martian mineral. They traveled from one world to another without engines or navigation, following nothing but the slow drift of orbital mechanics across millions of years. One of those meteorites caused a scientific controversy that has never fully been resolved. In 1996, a team of NASA scientists announced that a Martian meteorite found in Antarctica, ALH 84001, a rock that formed on Mars 4 billion years ago and arrived on Earth 13,000 years ago, contained structures that looked biological: tiny carbonate globules, polycyclic aromatic hydrocarbons, magnetite crystals of a form produced on Earth by certain bacteria, and microscopic tube-like structures that resembled, at least in shape, the fossils of nanobacteria. The announcement made headlines around the world. President Clinton addressed it from the Rose Garden. Then the scientific community pushed back. Each feature, critics argued, could be explained by chemistry alone. The debate has continued ever since, unresolved. The meteorite, still sitting in a laboratory at Johnson Space Center, still studied, still contested, still inconclusive. If life arose on Mars in its early wet period, and if life on Earth also arose around the same time, there is a possibility that the two are related. The same impacts that sent Martian rocks to Earth could have sent Martian microbes, if any existed, embedded in those rocks, protected from the radiation of space by the rock itself, surviving the long journey and the fiery entry into Earth's atmosphere. Life on Earth might have a Martian ancestor, or life on Mars might have been seeded from Earth, or both worlds might have been seeded from a third source entirely, from organic material delivered by comets in the early solar system. The question of life on Mars is not separate from the question of life on Earth. They may be the same question, asked from different directions. Finding even a single fossil on Mars, even a microscopic trace of ancient biology preserved in rock, would change science permanently. Not because it would answer all questions, but because it would answer the most important one. It would mean that life is not a miracle. It would mean that the chemistry of living things, given water and energy and time, will happen. It would mean that in a galaxy of hundreds of billions of stars, each with their own planets, the emergence of life is not a singular accident, but a recurring event, something the universe does reliably, wherever conditions allow. Every assumption about our place in the cosmos would need to be revised. Every philosophical and religious framework that rests on human uniqueness would need to expand to include the possibility that we are not alone, that we have never been alone, that the universe has been alive for far longer than we knew. Not finding life on Mars would also change everything, but differently. If Mars had water and warmth and chemistry and time, everything that life needed on Earth, and life still did not begin, then the emergence of life must be harder than we think, more improbable, more dependent on conditions we have not yet identified. The silence of Mars would tell us that the gap between chemistry and biology is not easily crossed, that whatever happened on Earth to produce the first self-replicating molecule was not inevitable but accidental, not common but rare. A Mars with no life, having had every opportunity, would make the living Earth feel more precious and more lonely than we have ever allowed ourselves to feel. Two equally significant discoveries, two completely different universes revealed. The methane in the Martian atmosphere keeps returning to this question. Mars should have no methane. Sunlight destroys it quickly, and without a source continuously replenishing the supply, it should be absent from the atmosphere entirely. Yet instruments aboard orbiters and rovers have detected it repeatedly, in amounts that vary with the seasons, appearing and disappearing in patterns that suggest an active source somewhere beneath the surface. The most mundane explanation is geological. Certain reactions between water and rock produce methane without any biology involved. But the most extraordinary explanation is also on the table. On Earth, the largest source of atmospheric methane is living organisms. If something beneath the surface of Mars is producing methane today, we cannot yet rule out that it is alive. The search for life on Mars is, in the deepest sense, the search for our own origins. Every mission we send, every sample we collect, every instrument we press against ancient rock is really asking a version of the same question we have always asked about ourselves. Where did we come from? Are we alone? Does life happen because the universe tends toward it, or despite the universe indifferent to it? Mars is the nearest laboratory for this question, close enough to reach, old enough to remember a time before the answer was clear, preserved well enough to still hold evidence of whatever happened there. We are not exploring Mars only out of curiosity or ambition. We are exploring it because it holds something we need to know, something about the nature of life itself, and whether the fact of our existence is ordinary or extraordinary, expected or miraculous, shared or utterly, terrifyingly alone. Mars is the first step beyond Earth, and that is not a small thing. For all of human history, every person who has ever lived has been born on this one planet, breathed its air, lived and died under its sky. Every civilization, every war, every love story, every scientific discovery, every piece of music ever written, all of it happened on a single world, orbiting a single star in one quiet corner of a galaxy containing hundreds of billions of others. Mars would change that. Not immediately, not easily, and not without cost. But for the first time in the history of life on Earth, there would be humans somewhere else. A second place, a second chance, a second story, beginning on a second world. That is what Mars represents, not a destination but a threshold, and everything that crossing it would mean for what we are and what we might become. The Moon is where we practice. Mars is where we begin. Everything humanity is doing on and around the Moon in the coming years, building habitats, learning to extract resources, understanding how the human body responds to long stays away from Earth, is preparation for something further. The Moon is close enough that a problem can be solved with a 3-day journey home. Mars is not. The skills learned at the Moon, the technologies tested, the physiological data collected, all of it is rehearsal for a mission that will not allow the same margin for error. The Moon is the classroom. Mars is the examination. And beyond Mars, further out into the solar system, lie other worlds that will only become reachable once we have learned what Mars has to teach us. What we learn on Mars will carry us further than Mars. The engineering developed to keep humans alive on the surface, the life support systems, the radiation shielding, the closed-loop resource management, the psychological frameworks for small crews in isolated environments will apply everywhere beyond the inner solar system. The fuel production technology proven on Mars will work on other worlds with similar chemistry. The medical knowledge gained from years of human presence in low gravity will inform every future long-duration mission. Mars is not the end of the story of human exploration. It is the point at which the story stops being confined to a single solar system neighborhood and begins to expand outward into something larger than any generation before ours has been able to imagine from a position of genuine possibility rather than pure dream. The first person to walk on Mars is alive on Earth right now. This is one of the most remarkable sentences it is possible to say in the early 21st century and mean literally. Someone alive today, perhaps already selected, perhaps still in school, perhaps not yet born to the career that will take them there, will one day stand on the surface of Mars and look around at the red plains and the amber sky and take a step that no human being has ever taken before. They will feel the gravity that is lighter than they grew up with. They will hear the silence that has no equivalent on Earth. They will look up and find a blue star in the Martian night and know exactly what it is. That person is here, now, somewhere on Earth, living an ordinary day with no way of knowing yet what their life will become. Mars does not need us. This is important to say clearly, without romance. The planet turned for billions of years before life appeared on Earth, and will turn for billions more after whatever we build there has faded back into dust. It does not wait for us. It does not welcome us. It offers nothing freely and takes back everything eventually. The storms will bury what we build. The cold will test everything we bring. The silence will outlast every voice we carry there. Mars is indifferent in the way that only geological time can be indifferent. A patient beyond any human scale of patience. Old beyond any human scale of age. We will go there not because Mars needs us, but because we need it. We need the challenge of it, the humility of it, the perspective of it. We need to stand somewhere other than Earth and look back at the only home our species has ever known and understand for the first time from the outside what it is we are so fortunate to have. And now the journey slows. We have traveled a long way tonight, across a surface older than anything alive, through rivers that ran dry 3 billion years ago, alongside robots that crossed red plains in silence for years before going quiet themselves. We have stood at the edge of what it would mean to leave Earth behind, to breathe air that was made rather than given, to look up at night and find a blue star where home used to be. You have heard of a world that is rusting in the dark and breathing faintly still, a world that once had water and may have had life, and has not yet given up all its secrets. A world that the best instruments we have ever built are only beginning to read, one sample at a time, one season at a time, one Marsquake at a time, in the slow, patient language of a planet that has been keeping its own record for longer than we have existed to ask questions. And somewhere in all of that, in the dust storms and the frozen poles and the ancient lake beds and the hollow lava tubes waiting beneath the surface, is an answer we have been trying to reach for as long as we have looked up at that rust-colored light in the night sky and wondered what it was. You are made of the same material as Mars, the iron in your blood, the calcium in your bones, the oxygen you are breathing right now, as you drift towards sleep. All of it was forged in stars that died before our sun was born, scattered into the cloud that became this solar system, gathered into worlds. Earth kept its share. Mars kept its. The same ancient chemistry, shaped by different gravity into different outcomes. One world that held its warmth and grew oceans and life, and eventually people who would look across the dark and recognize a neighbor. One world that lost its warmth and grew cold and still and waited. Tonight, Mars is still out there, still turning, still holding its ice and its ancient rock and its quiet, unanswered question. The dust is still moving across the plains. The temperature is still swinging between midday warmth and midnight cold. Somewhere on its surface, a rover is sitting in the dark, its instruments patient, its sample tubes sealed and waiting. And you are here, on the one world in this solar system that kept everything: the water, the warmth, the air, the improbable chain of events that led, eventually, to something capable of wondering about all the rest. That is not nothing. That is, in fact, everything. Let the images settle now. The red plains, the blue sunset, the earth as a star. Let them drift the way thoughts drift, when sleep is very close, not gone, just softened, just becoming something gentler than thinking. If these slow journeys give your mind somewhere beautiful to rest, consider liking and subscribing to Sleep Science Daily. It helps others find their way here too, one sleepy soul at a time. And if you happen to still be awake, another journey is waiting for you. But for now, you do not need to go anywhere. Let your breathing ease. Let your jaw unclench. Let your shoulders sink down into wherever you are resting. The universe is continuing its long unfolding without asking you to keep up. Mars is turning slowly in the dark, and you are exactly where you are supposed to be. Sleep well. Good night.